Okay, I think we're ready to go. Fantastic. Well, thank you for joining us. We're almost at the end. We're very close. So I promise I'll do my best to make this short, sweet, but exciting at the same time. So I'm here as the lead-in for Nicola at Framatome, right? I'm your lead-in guy. So I'm real excited to be here. I'm from Houston, Texas. I am 29 years in the market here at, let's see if this works. Is this working? All right, now it's working. So 29 plus years in the industry. It's actually more than 30, but if you say 29, it sounds a little bit less. I'm the head of global strategy for Siemens. A lot of questions come up as to, with Siemens, is it Siemens Energy? Is it Siemens Digital Industries? I'm with Siemens Digital Industries. So we are completely separate from Siemens Energy. And this is where we are in this family of companies that makes up Siemens. Let's look at the world that we're in. We know that things need to be more powerful, but they have to be greener. We know we need more supply, but it has to be consistent. We need more throughput, but we need lower cost. And we need to be more productive, but we also need to be sustainable. So with these influences, we're seeing for years now, we've seen the policies that have come out, the innovation plans, right? The thematic plans from companies, from countries, from states, provinces, and so forth. So there's no shortage of commitment in this space. And from my perspective, we're seeing all of the oil and gas, all of the companies across the energy spectrum are in fact now thinking of themselves as energy companies. So we're seeing a tremendous transformation right now. My viewpoint, nuclear energy is a key to the clean future as we go forward. I want to make that very clear. I know sometimes when you look at Siemens, sometimes there's a question. Let me be very clear. Nuclear energy is a key to that clean future. And let's look where the money is going. Right now, if you look at the EIC, the Energy Industries Council, back in 2016 when I joined Siemens, we took a snapshot of what was currently in planning or execution or decommissioning throughout the energy landscape. You had across the globe over $10 trillion in investment. That's now increased to 13 trillion, and as you can see, it has really shifted into clean energy tech. Now I know the next question is, okay, but what part is nuclear? So if you look at the nuclear stage, you're easily well over $1 trillion in either new builds or decommissioning. And of course, I've come to France from Texas because this is the heart and soul of nuclear. And look at this, another indicator. Look at the private equity that has flowed into nuclear fusion. So for us, nuclear is absolutely paramount to that clean future. And look, this isn't our first rodeo. This is not the first time as a species that we've made an energy transition. If you go all the way back to 1800 and before, and you come forward and you look at the rate of transition, look at this with nuclear. Nuclear has not yet even begun. We have just started a renaissance in nuclear energy. And I am very excited about what this is going to look like over the next year or two or three. And you know, I'll take a moment. I've heard some people say part of the problem is the slope of the line for energy. I would say that we're only going to see more demand for it. So it's that type of energy. It's where are we getting our energy from? I mean, if you imagine nuclear coupled with hydrogen production, imagine the clean footprint you've just developed on the global stage. Incredibly powerful. So nuclear, but what I want to also talk about before we get to you, Nicola, and you start talking about industrial uses of CFD, I want to talk about a slightly broader context for which simulation is key for. And it is incredibly important that we have a life cycle approach to nuclear. Now, why is that important? Because when you start looking at where the challenges are for us when it comes to all of this capital that's deployed and making sure that it's used effectively, because we cannot afford to misuse the capital being put into nuclear. We have to look at the fact that anytime you are doing build processes like greenfield construction or brownfield construction, which can incorporate debottlenecking or turnarounds or expansions, all of those have these issues. There are no shortage of reports on the problems we have across industries when it comes to capital projects, when it comes to using that capital effectively. We're not on time. We're over budget. We have bad quality. Why is that happening? Well, I'll tell you why that's happening. Because when you don't have your requirements solid at the beginning of the life cycle, those problems go into design. Your design and simulation suffer from that. If those aren't done effectively, then what happens? All the problems are in construction, come to life, and everything blows up. And change management during construction is the worst time to manage change. And it happens all the time. Our species has got to get better at doing this. And then construction pushes commissioning forward, or actually back, which then crowds startup, which then does what? It puts a lot of problems on operations shoulders. So this is typically what we've done. This is what we need to have. We need to have a solid life cycle, a solid physics-informed digital twin that represents the sum total of all the data, data sheets, drawings, documents, and models that were created, hello, computational fluid dynamics, through the process. We have to have that. Now, it becomes very complex, but it's not. If you create an elegant, not product lifecycle, but capital asset lifecycle management process, then you can bring all of the design from any third party. You can look at all that you have to manage through execution with simulation at the heart of that. And you need to make sure that you have a closed loop with whatever, and these are some examples of the mini ERP and CMMS systems that we have in operations. But you have to have all of this within a life cycle format. So when we have issues, which you're going to talk about during CFD, both in the design and in the optimization of operations, we have a digital life cycle around it. And I'll have a story to share if we have the time, or we can share it in the room back there. So I'm not going to steal your thunder so that you can talk about it. But when I talk about simulation, you know, we talk about improved economics for SMRs. You talk about reducing thermal fatigue, exploring sparger configuration, fuel performance, plant-wide performance, and optimizing spent fuel storage. All of these represent how we can turn that life cycle into a solid, well-performed design, build, and operate environment that Nicola is going to talk about, that he's at the heart of. So again, when you come back to this, we have to be mindful that when you're doing simulations, we have to do it in the context of a broader life cycle mindset, a manufacturing mindset for us in the field. In fact, Brian Ferguson, who used to be the CEO of Synovus, when we had the last downturn in oil and gas in 2015, and everybody was losing money in energy that was in the oil and gas business, his statement was, we have to apply a manufacturing mindset to capital projects. We have to take that same detailed life cycle view on assets and apply that in the field. And so now that's driving modular construction. Now that's driving a greater focus on simulation going forward. And what excites me the most is I'm standing here in front of everybody in an industry that is bent on developing a new model. So all of us are students of Buckminster Fuller. All of us are rethinking, how do we actually drive fabrication, align it to requirements, make sure it's adherent to the simulations we did, that the simulations you did are now implemented in the field with that process simulate. We are here, all of us, building a new model, and nuclear is the new model for our species going forward. And that's what excites me. So while I like to say it's a nuclear renaissance, my colleagues like to say it's a nuclear revolution. And it's not started, it's actually accelerating. So it's been my pleasure to come here, be the lead-in for you to talk about industrial uses in CFD, but I want to make it very clear. We are committed at Siemens to nuclear. We are committed to making sure that those capital dollars that are invested wisely and executed correctly. And it will start with your industrial uses. Over to you.
Thank you. I will just switch computers.
Right there.
Okay, so I'm from Framatome, and I will just speak about why do we consider CFD for nuclear design, and then give you a quick overview and some examples. So why? So the background is that in the past, when we designed the French fleet, okay. in the past, when we designed at least the French fleet, we used a lot of testing and 1D analysis because that was all that was available at the time. But now we have new challenges. The regulations are getting more and more strict, and there are new constraints regarding the demonstration of safety. It's not the safety by itself, it's the fact that you can, with a very rigorous way, demonstrate the safety of the plants. So that means that you need to go much more into the details of what is happening inside the plants, and also the complex physical phenomena that are taking place inside the plants. That means that you cannot use 1D systems for everything anymore, because there are some mixing zones, there is some stratification, some stuff that these codes are not designed to take into account. And you cannot rely on testing anymore as well, or only on testing, because testing is slow and it takes a lot of money. So we need to have a tool to examine in detail the physics of the reactors and to have a quick and accurate answer. And this tool for us is the use of computational fluid dynamics. Okay, so the use, oh, sorry. Yeah, just trying to get back. Okay. The use of CFD in Framatome is an old story. We have more than 30 years of experience in the industrial use of CFD. That means at the service of industrial projects. We have more than 70 CFD specialists, large expertise on a variety of topics. I will show you on the next slide. And we have also our own labs. That means that we are able to perform some dedicated experiments to check that the computations that we perform are in line with the physical reality. We use industry software such as Siemens Plus from Siemens, and also we have access to EDF supercomputer called Kronos. It's a huge computer. We have about 1/3 of this computer for Framatome, so that means that as we speak, there are 10,000 CPUs dedicated to CFD analysis for the design of nuclear reactor running, actually. So a general overview of what we're doing. If you look at the nuclear plant at the center, we perform first some CFD analysis of what's happening inside the fuel assemblies. So inside fuel assemblies, we're looking for pressure drops, mixing, also the capacity to catch up the debris inside the bottom nozzles, as well as fretting. Then we also perform a set of computations that are dedicated to the design of the internals of the reactor pressure vessels and the primer loop. So the bottom part, the top part, also the control rod guide tube assemblies. That's a big part of our activity, but we are also involved into a lifetime extension justification. In order to do so, you need to assess with a lot of details the thermal loadings inside the reactor when you have normal or upset conditions. For instance, this is a representation of a change in the level of the pressurizer, so you have hot water flowing inside the primary loop, and you need to assess what it means for the reactor. We are doing the same at the level of the pressurizer. We are also working in the secondary side. We are performing some compressible flow analysis in order to assess the maximal flow rates that you can remove from the safety valves, for instance. We check that the design of the safety valve is okay. We're also working on the secondary side on issues on mixing inside the main feed water torus here or inside the downcomer from the steam generator. All of this means thermal loadings on the components, and we ensure that our components are fit for service for 60 years. But that was inside the pipe. But if you look outside the pipes, then we have also models for the buildings themselves. When you operate the reactor, there's a lot of heat that goes inside the building. During the outages, you want to get inside the building as soon as possible. So we are performing some detailed analysis to inform the people of what would be the expected temperature in the different rooms so that they can access as soon as possible. And finally, and that will be my example for later, we are also performing a set of computations regarding manufacturing simulation. There's a lot of money at stake during manufacturing. We need to have top quality components, top quality steel, and we are performing some detailed simulations of quenching, of oven heating of the components, and also of post-weld heat treatments of the components. So I still have a few minutes. Yeah, I will talk a little bit about thermal treatment. So when you're building a plant, a nuclear plant, you need to perform a lot of welds. And these welds will induce inside the pipes some residual stresses. That means that the pipes will be fragilized due to the welding. What we want to do is to remove these residual stresses, and to do that, we need to heat up the pipes on site at a temperature of about 600 degrees for about 2 hours. And if you do that, then you remove the residual stresses and you get back a pipe that is very strong. What's difficult in this is that when I say about 600 degrees, that means 600 degrees plus or minus something like 15 degrees. So that's very narrow. We have a very stringent specification. And at this level of temperature, 600 degrees, if you have any default in your thermal treatment process, then that means that you will have cold spots. And cold spots means that the residual stresses are not removed and you are not compliant with the standard. The other difficulty is that our components are very large. They are difficult to access because it's a process that you apply on site. And we have a large number of different heating equipment because we are working, it's a large construction site. So there are a lot of people working with different technologies. You have here some examples of the different technologies that are being used on site. And of course, we have no right for mistake. That means that we need to have the top quality steel at the end. So what we do is that we perform for each individual weld, we perform a single or an individual CFD simulation of the heat treatment that is performed after the weld. So for each configuration, you have different examples of configurations here. We will ensure that the heating process will deliver the temperature field inside the pipe that is consistent with the requirements. So it seems easy because here you see just the temperature on the pipes. So you're thinking, okay, this is very easy computation. The problem is that, in fact, these pipes, some of them are vertical, some of them are horizontal, there are some valves. So there's a gas inside. You cannot just come and plug the pipe because the pipe is what you need to install on site. So it's tens of meter longs and you have no access. You cannot plug it. So there is some gas flow inside the pipe. And this gas flow will disturb the temperature field inside the pipe. So that's why we need some detailed CFD analysis. So what we did is that we performed some steady state computation in order to design the heating process and to be sure that it's compliant. And we also performed some transient computations in order to assess what should be recorded during the treatment itself. That means that the people performing the treatment have before their eyes a curve of recorded data that is the expected value. And that's what you see here. That's the plain line here. That's what is expected during the treatment. And what's actually recorded is the dotted line here. So that was very, very close from the simulation. And in fact, it was so close from the simulations, and when we had a significant deviation, we could be sure that something was going wrong. We could shut down the heating, investigate, and restart with a solution, and you have a perfect heating in the end, perfectly compliant with the plan. So we did that for more than 100 wells. Now it's really fast. Actually, people think that CFD can be a very long process, but starting from scratch, just with the drawings, you get all the results within 10 days. And once again, you have a very good accordance with on-site measurement. And the final step is that we are so confident into these simulations that we are actually performing now a set of simulations beforehand by configurations in order to have a database of what could be the results if anything goes wrong. And from this database, we're being what we call a meta model or a reduced order model that can be delivered on site so that the people actually performing the heating have access to this information and they can make meaningful decisions based on 3D computations. Okay, so as a conclusion, when you use it correctly, you can really get much from CFD. It can better represent complex physics. It brings margins to the projects. It also answers to the call for a more rigorous safety demonstration. And we have a long and broad experience in this. We can adapt the models to the needs of the projects. We have validated tools, and it's fast enough. So if you're interested, you can come to me or go to the Framatome booth. Thank you.
If you can go back one slide. Yeah. When he starts talking about thermal treatment, it reminds me of a story, an analog, a parallel for us to consider here in nuclear. In 2010, in Northern California, Portland General Electric experienced an uncontrolled release. It had an incredible explosion. It killed 13 people and caused $8 billion worth of damage within a residential neighborhood. Now, I was part of a company that was part of the investigation into that. We sent out corrosion specialists as part of the team. And what we found was that there was crack propagation in the welds that led to failure. Now, the question then came up, what were the weld procedures? What kind of heat treatment was done? You know, when this was first put in, there wasn't this available tool, this ability to simulate in high definition the reality that we had to deal with. There were no records. There was no way to validate if the weld procedure was the failure, the materials were the failure, the training for the welder was the failure, the accreditation for the company that did the work was a failure. The list goes on and on. It is imperative that if we put the time and the effort to use Chronos to go in there and do the computational fluid dynamics, we're also capturing that as part of the life cycle because we don't want to have this. We cannot afford those type of failures in nuclear. We're in a tenuous place right now for this industry. We have to be successful, more than successful, because the world is watching. We don't need any more incidents. We need to focus, do this correctly, follow the guidance you're showing, and make sure that we're capturing all the data, documents, models, drawings, and data sheets that go hand in glove with this kind of work. I cannot stress it enough. So I'm excited when all of you come into the room right after this, because we're about done, and they talk to the two of you from my organization as well as us, Nicola. So I can't tell you how excited I am about the work you're doing on that supercomputer. Fantastic.
Thank you.
And thank you.